So for the engineering analysis for our CAM follower, this is out of the, what did I call it, Fundamentals of Engineering Graphics or Engineering Fundamentals. It's one of those. Some of the things that attract me to projects are, kind of looking at it and doing the design for manufacture, putting a scenario in place where we have a company that has one of these gizmos on their production line or has it in their shop, and whatever function it's performing, it's worn through its useful life. They repaired it. There's not much left. They need to replace it. So right now it's limping along and getting the job done, but at some point it's going to fail. And so in our design process, kind of setting up that scenario, I want to go through and build the pieces that are appropriate to bottom up, and then build some pieces that are top down. And looking at this base, I can't remember last time somebody asked me if I would send something out to make a casting. I know there are casting houses and there are people that are, companies that are capable of doing this base, but from a manufacturing standpoint, a CNC standpoint, I can build this in 4 pieces and end up with pretty much the same result and make it a little bit more manufacturable. Maybe even be able to control the tolerances a little bit more. So on the looking at this side where this boss that supports the bearing kind of comes through, there's no real relief. There's no seating of the bearing, and so those are some of the things that I want to address. The shaft is showing being supported by one bearing, and there's nothing really driving our cam back here. So there are failure modes as it is. We've got a partial design, and we're going to do our best to complete it. So at the very least, this needs 2 bearings to support that shaft. We don't know exactly what the materials are. At least I didn't see. The base was cast single roll ball bearings. Shaft, assuming it's going to be a steel or a stainless steel. And then springs, roller bearings, parallel keys, and keyways. So assuming a lot of steel. Right? So we'd like to do an analysis of, if this is a fairly low pressure, maybe I could get away with having aluminum and making this a replacement piece. This is a consumable item. Since it's going to wear out anyway, we do a 60-61, and part of your maintenance schedule is it's easy to make, it's easy to replace, and once a year it gets a new one. All right, maybe it wears out too soon. Whatever this is being raised into and tapping against, maybe it puts too much a load on this and it has to be a steel. Well, then what style of steel or what grade of steel? Probably not in the 1018, 1020. And if we're making things out of stainless and comparable stainless, probably the roller bearing is stainless. We would have similar metals that would have some similar wear rates. And we have to decide, is the bearing our consumable, the maintenance item? We certainly, in that case, if this is a big honking chunk of stainless, we don't want to replace this every year when we could replace the bearing. So decisions on materials come down to maybe this is a 440 series of stainless, harder, more wear resistance. And then the roller bearings are in the 300 series so that they wear out a little bit quicker. The other thing is we don't know what motor is driving this. And one of the things I would think I will spend a little bit more time on this weekend is to build this out where we pick a NEMA, 23 frame motor that we can control and figure out how to mount back here and have it coupled to this mass as we determine some of these engineering properties and build through. So in this discussion, all of these, kind of higher level engineering items, I don't know that everybody gets to see that, or at least at the floor level, you're not really thinking about, how all these items go together, but there is, either people or peoples that are building in and trying to accumulate these tolerances to make the geometry work and meet basic specifications, our life expectancy and runouts and and some of the other items. So the long way around was my point to all that was I'm looking at this boss thinking I want to make this a separate removable unit. And it can either attach to the rib or become part of the motor housing. But basically, when I get through, I want either a couple of flathead screws or socketed cap screws coming in from the back to be able to. I still haven't decided if I'm going to make it to where you take the cam. I mean, that would be kind of the best case scenario. Is that we would try to pull this whole thing out as a unit. Right, so there are some options there, and that is all going to drive some of those bolt hole patterns. How many bolts do I need to hold this, based on our loads and what we're trying to drive. So if I make a flanged unit and have it run through the backside and bolt into the housing to where you could take 4 or 6 bolts off of the back and the whole thing slides out the front, that would be optimal. The motor coupler, that's fairly easy to remove and maintain. So, that's not a hard plumbed type fit. All right. So, as usual, I pick a project and I'm thinking, I'm just going to do some simple run out on this, but it works out to be the profile on the outside. As I'm reading more through the 2018 standard, we said we're going to stay with the 2009. In reality, the companies and industry will take, anywhere from months to years to adopt. So 2018 will start to appear, but it comes back to the note that you put on that drawing, on that document that says this will conform to ASME ANSI Y14.5 2009. That is the standard that you're adhering to. That's what you're working from. And anybody reading that document should be adhering to that standard. All right. So that being said, one of the things that jumped out is in the 2018 is they're doing away with concentricity and symmetry, and they're basically replacing them with position. And from what I've seen of drawings coming into our shop, is it's already kind of transitioned that people are using the positional tolerance to replace those two anyway. So their notation was to try to remove or eliminate confusion, for those two notations. All right. So one of the things that I was looking for when we were doing the pulley and had to go back and find it was the chart in the Machinery's Handbook. I found my PDF version, and so those numbers that I was pulling for the pulley, I'm going to have to do pretty much the same thing. So a force fit or an interference class of fit is pretty much aligns to a light press, a heavier press, and then you get into you're going to have to heat this one up and cool this one down to get them to force together, and they're pretty much never going to come apart. So when I go into the cam and I'm looking at that 16 millimeter shaft, about 630 to 670, call it, we're going to be in this range for an interference of between 0.2 of a thousandth and 0.9 of a thousandth. So reading this value, the one that freaks me out every time I look at the notation is these are in thousandths of an inch. So 0.1 thousand, or where to go, 0.2 thousandths of an inch would be 0.0002 and 0.0009. Have to count zeros there. All right, so not a whole lot of interference, but enough to stabilize and keep this thing, this shaft running. All right, so the geometry, base circle of 146, there are no dimensions on this. They're just giving us specifications. Face width of 16 millimeters. The rise 10 millimeters, harmonic motion, 90-degree dwell, and then, or in 90-degree, dwell for 180, fall 10 degrees. Basically, it says that the center of this circle, the shaft is going to sit 10 millimeters off of center. That also brings up rotational mass. Right, so something that can affect our tolerance, or eventually will, as this thing wears and goes through its product life cycle, comes back to how fast are we turning this? If it's 10 RPM for the next 10 years, we're probably not going to see a significant amount of wear as long as the lubrication schedules, basic maintenance is performed. But if this is spinning at 1,000 RPM, all of a sudden we've got an unknown mass. Probably when we get down to it, if we make this 16 millimeters thick, 140 millimeters in diameter, we're talking about 5/8 by a little over 6 inches. We're talking about something that's in the neighborhood of 3 to 5 pounds. All right, so we're talking 2.5 kilograms, maybe 3. All right, so that's some of the things that we're going to enter into this design with, is thinking about our tolerance, but also on the other side of it, what are the operational parameters that we want to work with. All right, so I do like to think of this as as those levels that you're going to have to contend with all the way from concept to production to assembly, inspection, all the way out to the final end user having to maintain this piece. All right, so this is going to be interesting. I don't think I have my, I'm used to having my dual monitors, so base circle of 146. I may pause here for a second and see if I can get this on my other screen. Okay, so a couple of things of note, I guess, before I get away from that one. Just kind of reading through the cam parameters, bearing overall dimensions, spring parameters. We're going to go out to Mcmaster as a source for these items. Got a couple of good charts and tables, and items from Misumi is another available. So if you want to replace or look for other items, there are multiple places to pull from. All right, some are going to have better ordering, identification, those types of things. All right, so where did that go? Zooming down to, all right, so the follower and the follower width with the square key. I'm assuming that that is this piece. And then the bearing dimensions, 17 millimeters by 40 millimeters by 10, and then a 4 by 13 by 4. Assuming that would be the small one. And then if we're looking at a bushing, kind of have a couple of options to put a bushing into the top center of the piece. So we're going to go with currently available items, not knowing when this was originally created. So that was what I was looking for. So one of the issues is if I don't think we can zoom up on it that great, but you can kind of see that says 16 millimeters on the shaft, but we just said the bearing was 17 millimeters. So either there needs to be a step, or this isn't a complete shaft drawing. So the other thing would be, as this goes through, let's see, we're showing the shaft, the keyway going through the bearing. Well, if that's going to be a press fit so that we can maintain that that rotation, then the other thing is, how is this being retained so that it can't move if it starts to wear or lose that press fit, and it's spinning at 10 RPM. I'm not worried about it falling off. At 1,000 RPM, it becomes the saw blade slicing through everything. Then it's a little bit of an issue. So I do want to build in some safety where there is either eclipse or retaining or some type of step. So that gives me the opportunity with a 17 millimeter bearing to step this down to 16 millimeters going through the cam, and then putting either a standard washer and a kind of like what we did on the axle for the pulley, a button head or something that will provide some retention and compression to that for the cam. All right, so that being said, I jumped over into Mcmaster, And one of the ones that we're looking for is a spring, and I'm interested in pretty much what it's going to be doing with our loads and the rates pounds per inch. All right, we can convert those over pretty easily. So we have a spring parameter wire of would be a 1/16 of an inch, and we need to come up with a wire diameter. And what was the length? Inside diameter at 9 millimeters would be about 375, and 55 on the wire. We're pretty close there, but the overall length of 20 millimeters is going to put us up at like 787. So 3/4 of an inch, 781 would be a little bit closer. So I don't really see anything in the 1/16 range there. And I don't see anything in the openings. So let's go back to the 3/4 inch. And I think if I pick the bushing that I want, I'm going to end up losing some of that travel anyway. So let's go with the ID and 062. So 62.4 pounds per inch. That's a little stiff, right? So I'm not sure, what exactly we're trying to keep in contact or what we're pushing against, raising up and down, but that seems a little bit on the high side. But that's the specification, or that's as close to the specification as I think I'm going to get until we get something that is a little more definitive. Let's see what we can find with that geometry. So we'll get a product detail on it. I want to do the same thing that I did previously, and so max load of 23.4 pounds, and we're not quite an inch, so may not max there. So we'll print that one out, and it looks like I'm going to have to need to start my document folder anyway. So we'll make a cam follower project, and under the cam follower, then I'll set up my documents, if I can spell documents. There we go. All right. So even if it turns out that I'm not okay. All right, I'm not sure what's going on. All right, well, we have a compression spring then. It's probably going to be easier to do the screen clipping then. That's going to be the case. All right, so that's kind of a first try. There's since there's a model for it, then we'll go ahead and save the SolidWorks model. That should be going to my downloads. And while it's doing that, we'll jump over into the bushings. So on the shaft, part of the subassembly. All right, so item 2 here. Again, that would be kind of a stainless or something that has a little harder wear resistance for the bushing. It's given with an M5 at the end and a diameter of 8 millimeters. All right, so we need something that I did select for a metric so that we would be staying in that group, and an 8 millimeter shaft. The housing of 11 millimeters, 10 millimeters long. I believe that one's going to work fairly well. If we go back up to the flange that it's seated in, and say there's 10 millimeters there, and if the flange height sticks down a little bit, that takes up some of that room in the that we lost from the length of the spring. All right, so if I grab that one, and we look at its detail. I'm going to try and print one more time so that we can have these. And you're going to bark at me again? No? All right, we'll try and save the bearing again. All right, so while it's doing that one, then we'll look at the bearings. So since this is going to be a kind of a permanent installation that really until the bearing fails, I don't want to have to change it out. So our specification was for a 17 by 40. All right, so a 6203 and 12 millimeter width. Theirs is shown as 10, so we may have to make the adjustment since I don't have a lot of selection. Oh, that was the open. So the thing with the bearings, the open, is that it's going to be exposed. It's going to be able to transmit heat better, but we're going to have to provide a little bit more in the way of lubrication. So we come down to the sealed, and the 17 by 40, 12 millimeter thick. Dynamic load of 1,800 pounds on the radial. I think we're pretty good there. Static of 980 and max RPM of 10,000. Wow, that thing's going to be zinging if we hit 10,000 RPM. So we'll grab that one. And again, I want to just grab the print. And having these specifications to work back from, at least at hand, that we can find the manufacturer's tolerances pretty easily. That's going to help us out a little bit later. All right, so I need to back up out of those. Let's see, the other one is a ID of 4, OD of 13. And I think even the one on the cam follower, I want to stay with a sealed bearing. And so we're looking for, let's see, that one shifts over. And we're going to have fun finding that one. So shaft diameter of 4 by 13. So not quite half an inch. And 3/16. All right, so we're going to have to do a little more digging on that style of bearing. All right, so 13 millimeter OD, thickness of 4 millimeters, ID of 4 millimeters. So just in the list, I'm not getting anything close, which means that we may be going to a more specialty item. The choice is: do we buy something off the shelf, or does it really need to be at that level? So just to have a replacement handy, 4 millimeters would be about 5/32, 157 thousandths. I don't see too much of a problem going up to a 1/4 of an inch. The 13 millimeters would be a little bit over half an inch. And so 5/8 would be closer to 15 millimeters, so we're gaining about 2 millimeters on the diameter. Again, that affects the stack up. So just to have something to work from, though, we'll go ahead and grab this one. And I'll go ahead and print the page. Printing failed. Really? So the troll's still trying to print the other one? Yeah, I didn't like that one. All right. Well, let's see if we can at least save the item, and I'll have access to the part number. So if I can get the other information out of it, we'll work from there. Okay. Oh, file is being distilled. Are you sure you want to quit? No. Oh, another one with yes. All right. Well, that's fun. So it was still doing the oil embedded. So not sure what the issue is. I guess probably because they have the links back to the website embedded in. I still don't like that one. Okay, well, I'll come back to that one later. All right, so either I hit that one. Oh, there it goes. So it got the flange, it got the shaft. All right, I'll give it one more shot and then we'll call it good. Hey, how about that? All right, so we'll let it finish on those. All right, so I'll have to double check what's going on with those. All right, so for our cam follower project, if we're going to have top level assemblies and assemblies, then we'll probably need at least a little bit more in the range, and it's not always clear what is going to be the breakdown of assemblies and sub-assemblies. And nope, need to go to that one. So another new folder for the cam follower, just to have some place to start the process. All right, so I'm doing this in 2017 because I didn't think about having overwritten my 2018 with 2019, and 2019 will cause you some small amount of headache to load the files, where 2017 will just come in and upgrade. So we'll stay with that one, and we're going to be in a part metric, and hopefully it will catch up. Oh, since the 2019 overwrote the property tab builder, it's telling me that anything I put over here as part of my template process, I don't know that we're going to track those out that far, but we'll hold that one in reserve. All right, on the front plane then, my sketch, I'm going to put in the 146. All right. One of the things that we haven't done with these is if I edit the document units and go back to, I believe it's dimensions, if you would like to see the dual dimensions, to me they're just numbers. Working in metric, working in inches, can convert fairly easy. So if you would like to have both turned on, then it will show the metric on top and the inch in parentheses underneath. That'll give you something to reference to if that's helpful. For the shaft size, I'm going to stay with the 16 millimeter going through, and then checking to make sure that I've got this oriented vertical. Then I'll set the 10 millimeters on the lobe. All right, so if that's 10 millimeters off as this travels around, then it should raise or lower accordingly. Next question would be, which way do I want the square key? We're doing 5 millimeters by 5 millimeters, which is pretty close to 3/16 by 3/16. That might be worthwhile jumping back into find key stock and just check the availability. So jumping over to metric, 5 millimeter by 5 millimeter, oversized on the tolerance. All right, so that should work out okay. And if I remember correctly, we want the rectangle. So when I do key stock, I pretty much am going to pick the midpoint. We'll set it vertical to the origin, or could set it vertical to the center. And then I also need the midpoint to be coincident to the circle. All right, and then we'll set our dimension, 5 millimeters. That seems awfully big for a for a 16 millimeter shaft, but if that's what they want to drive it with, okay. All right, so when I go to extrude this out, we're going to give it the 16 millimeters. Because I have overlapping entities that I did not go back and trim, and I don't really care about trimming them, because once I pick in the region, it is going to pick up that geometry, and we can go ahead and set. All right, so one of the first questions that I had as far as this geometry pretty much came back to, what does it weigh? So if I edit the material, I said we were going to try for a, it would be, if the wear would support the aluminum, that would be great. Don't want to go into the chromolys, and I don't see a 440, so let's just get a rough estimate with a 304. All right, so I think 304 would still have that decent range of wear resistant, maybe not as much as the 440, but it'll give us a good starting point. And then close. All right, and then under evaluate, we'll go into its mass properties, and we're, well, not too far off. 2,000 grams, we're right there at 2 kilograms. All right, so still a pretty good rotating mass. The other thing is that our center of mass, shown as the boss there, that's actually not too far off. We have a y dimension. Let's see, pull that out. And the y is the up and down of minus 0.122. All right, so 0.1 millimeters, which now I have to do the conversion, should be about 4 thousandths. That's really hard to justify trying to balance out. Z I'm not worried about because we extruded in one direction. If I had gone mid-plane, that would have been 0. So I think I'm going to overlook that one. And the looking at the start and stop on the motor for the rotating mass, that may still be a bit of a concern. All right, so that becomes the cam. Oh, and that went to downloads. See if I'll find my drive. Okay. Right, then the shaft. So in the stack up on the mechanical design side is really I need to have the frame available to build up this geometry. So I think I'm going to do that one next. The shaft, and we talked about the steps and retaining. We'll save that for later, so I can just close that one out. And so the base, what do they call that one? Just the base. I'm going to do as a multi-body part. So one of the advantages of multi-body is I can draw this in its current state. And when we look at the stack-ups of tolerances, we're tying these items together. And anything that is a mounting or a through hole shares the same geometry. So let's go into, my natural tendency would be to make this a 3D sketch. I don't know that it needs to be that complicated. So we'll start with, we can put that on center. All right, and then let's take a quick look. So we're accumulating these up. We have 15 millimeters on the base, and then 15 millimeters on the width. So we'll stay with those. And the length then. bring that back. Looks like 155. All right, so if I wanted this to show dual dimensions, then I'm going to have to do this on every part. So I'm not really that concerned about it. One of the things I shy away from is overlapping the lines, but we'll see what it does. If I needed to, I could window pick and grab just that line and delete it. So as long as I know it's there, that I'm going to maybe have to contend with it, then we'll go ahead and leave it. The overall was 269, but the length minus the 10 millimeters for the cap, we will go 259. And I can always come back and add that in later. 15 millimeters for the width. Location looks like about 60. Well, 80 off the back will work. And then if I wanted to see what that was for reference, it should add up 60, but still it's going to be a driven dimension. One of them has to take precedence. So even though it shows both, we're not going to end up with both. So because it's a casting, that may be a result of the decision they made for the casting. All right, so I'm not putting the radius in, but I am going to tie these together. And so this piece was 15 millimeters or 10 millimeters. Got 15 on the brain now. And it has a width of either 60 or 80. So I'm going to have to zoom up on that one a little bit and see what we get. If it turns out that we can refine it, then I'll pick it up. All right, so my goal in doing this is to generate a layout sketch that has all of the geometry that I'm going to need, minus the through for the bearing housing that we talked about. And well, we'll see how that one works out. I'm not entirely sure that this is going to stay an angle or that it's going to support the bearing, but I do need some kind of rib or structure that will help stabilize the vertical component. So whatever we've got there for 80 millimeters, we're just going to make it a 45 degree, if I can pick. And that will give me enough geometry for my layout sketch. All right. So when I create those sketches, I always like to rename. So a single click and kind of a pause and another click will let me rename it. So all of the other geometry, all the other sketches coming off of this will come off of this base geometry. All right. So we had the 155, looks like 130 on the width. All right. So on the front plane, we open up the sketch, and now I'm just pretty much tracing over the existing. And I want to do this as a mid-plane. So I think I mentioned this with the top down, is that we're investing time up front to create these layout sketches, go through the process. And then the payoff is that the building the model side goes pretty quick. So the mid-plane gives me that geometry. And then here's the difference between creating this as a casting, and one of the advantages will be that I could go back and forth on this geometry. But one of the advantages is that I will end up with 4 separate pieces here at a minimum. Okay, so opening up a sketch on the front plane and picking the next item, then extruding the base. And we'll do the mid-plane. Not entirely sure that it will stay at 130 millimeters. I could do up to vertex, up to surface. I'm going to limit how much I tie it together, though. And then the key here is that I uncheck the merge result. As soon as I uncheck that merge result, I end up with a separate solid body. So on my solid body list, I will have boss extrude 1, boss extrude 2, and I will come back and name those later, so they have a little bit more functionality to the mix. All right. So since there is a little bit more geometry here, I do try to group these, and if they get complicated enough, I'll actually create a folder and say, you know, this is the vertical, or you know, the whatever we decide to name it, and consolidate those items. So I think at this point, since I didn't include it in the sketch, I'm going to go ahead and create it. So we'll hide the sketch because I don't really want to tie anything to it just yet. And opening up a new sketch. Pretty sure that comes down tangent. So a radius of 65, yeah, that would be 130. And then from the base up comes 135. And I don't think that came up tangent just yet. So select and control select. Make sure that I have the edge. We can go tangency. No. And then both sides will need to be tangent for it to tie together. All right. And then the width is 40. So that one can go to mid. And I'm not sure what that was. I clicked through it too fast. Have to go back and watch the video to see what the error was. All right, so interesting part here is, can I make the cuts on these outside just with the geometry that I have? So if I go into the features and do an extrude cut, it already knows that there is material removed, and I want to tell it up to next. All right, so there's an available region, there's an available region, that will remove it and give it the geometry. All right, so from a cost standpoint, manufacturing these parts, if I left this rectangular, it would certainly be a lot cheaper. Removing this out is going to add machine time, is going to add processes to it, but I don't know what the relief is. So with the cut extrude, downstream issue may be the interface with this little L shape at the top, but I'm not too concerned about it getting tied into the other geometry. All right, so if I start tying this geometry in, though, I'm pretty much going to start a chain of events for our geometry to you know, kind of what I'm trying to say, have that associativity between the items. So 40 millimeters on the base, and I think I just want to leave that sketch for reference. If I make that a flange, how about we just leave that one for construction geometry for reference. Let it catch up. And I don't know that I'm going to end up being at 90, but we'll go ahead and cut up to next, or through all. Okay, so if I have a flange, it can connect. All right, that gives it enough geometry to give me that start. Want to show the layout again, and in my sketch on the front plane, I'll just trace over for the gusset. And since everything else is 15 millimeters, we'll go ahead and leave that 15 millimeters. Mid plane 15. Go ahead and accept. All right, so at that point, we're going to see what happens because I didn't uncheck the merge result. And it returns, even though I should have had 3 solid bodies, now it returns to 1. So that count is kind of keeping a relative position for me. And so if I unmerge that result, now it goes back to 3. And I hid something there, so that means that I'll go back and show. All right, so breaking in just a little bit at the 45 degrees. Don't know that that's that much of an issue, but it gives me a chance to address it and make the build. All right, so one more on the front plane, and then we can start putting in some fasteners. Okay, so a trace over the top, and then features, we're going to extrude. I'll stay with the mid plane, and that's going to end up being 40. We'll go ahead and accept. All right, so by the time I figure out the housing and what I want to do with this, at some point I should save it. That would probably be a good way to go. And this is going to be the base, kind of a sub-assembly. So and with the master model or multi-body parts, a lot of times I don't want to get it confused with metric, but kind of the designation master model, multi-body, MB, MM. All right, MB. So this is going to be the parent of those 4, 5, 6 components, whatever we end up with. And I merged it again, didn't I? All right, so since I didn't see a line here, those aren't separate parts. It's treating it as if it was one. All right, so I'm going to edit that feature and go back and uncheck the merge result. So a lot of times what I'll do if I'm making a lot of multi-body parts is I will hide these items as I go so that it doesn't see that it can merge them. And that gives it some opportunity. All right, so let's start with the base. And we need to be looking at that from the bottom. I'll do hidden lines visible. And so for 15 millimeters, we could go up to maybe well, we're going to stay in metric, an 8 millimeter, 6 millimeter. Probably don't need 10 millimeters, but then again, it's a 2 kilogram rotating mass, so all of a sudden 10 millimeter bolts don't seem that bad. So picking the bottom face, I'm going to use the S key to go into the hole wizard, and we'll see what a counter bore. So the choice here is the counter bore is going to allow this to float. If I use the countersunk or the countersink screws, then they're going to kind of self-seat and self-center based on where the manufacturing process put those countersinks, how it tied in through the holes. My intention is to use, well, I don't know that we'll go with as far as metric dowel pins, but either 1/4 inch or 5/16 dowel pins to locate the vertical to the base. All right, and then we have that stack up of looking at those conditions of what happens when we have the press fit on the base and the floating side on the vertical component to make the assembly. So I think I still want to stay with the counter bore. As a general rule, the diameter of the thread is also the height of the head of the socket head. So a 10 millimeter socket head will have a 10 millimeter high counter bore that is going to leave 5 millimeters on the base. Right? Again, we're talking even if these are mild steel, even if these were aluminum, I think the 5 millimeters is probably structurally sound enough to stay in that mix. All right, so pick up the counter bore. This is going to be an ANSI metric, and then we'll pick up a socket head cap screw, and size was an M10. And the nice thing about the hole wizard, it's not that big of a deal. It's not a great jump to get it back to an 8 millimeter or something a little bit smaller. All right, so if we show the custom sizing, 11 millimeter as the through hole, that's going to give us quite a bit of positional, 18 millimeters and 10 millimeters on the depth. So it's pretty much what we called for. And if I go 3, trying not to tie those up too much. Question then is, do I stay with the 10 millimeters since I chose that? 2 into the gusset seems kind of extreme, but I don't want the gusset to rotate. And as part of the assembly, when we look at the stack up, the vertical can be pinned, but then how do we assemble? The gusset really doesn't need to be pinned vertically. I don't know that it needs to be pinned, even horizontally. So, for the support and everything that it's providing, the perpendicularity that it's providing, I don't know that we need to make it quite that big. All right, so let's find a location. So let's see, was the layout still on? Nope. Let me see if I can show that. All right, I don't know if I'm gonna be able to pick that up quite, but let's see if it will allow me to center. So it doesn't like that one. Nope, still doesn't like that one. So what I'm trying to do is just pick that one line that I created, and not really going to succeed at that. So we've got the coincidence. All right, we got 2 of the 3 to line up. All right, so that being the case, well, until I have a better tool to use, I'm going to come off of that point to that point, and then use that to make a midpoint to a line. And then we'll stay with another center line off of the width. And, oh, actually I don't need that one. We have the midpoint. And I will set those to be horizontal. And then we just need some locations. So 18 millimeters, probably 25. And then from the outside, and we'll give it 12 and 12. Okay, so go ahead and accept that. I did not give it a feature scope. So one of the things to check with the solid with the multi-body solid bodies is right now the selected bodies are boss extrude and the cut extrude and the boss extrude. I don't think I need, well, I know I don't need all of those. So I'm going to clear the selections and make it just through that base component, boss extrude 1. All right, should it get deep enough or have enough connection to interfere with the others, then I'm not as prone to tie those in. All right, so figure out where I'm looking at the bottom again. Oh, I needed to do that as a fit. So another S key going into the hole wizard, and I want to make that a through hole. And let's see, where is said I'm not entirely sure that I'm going to go all the way with the metric on that. Drill sizes, if we go with the dowel holes, then I need to pick a size. So if we go with 5/16, 8 millimeters, then we have a clearance, a transitional, or a press fit. So on this side we'll have the press fit, and when we pick a class of fit, then this is where we're getting into the G's and H's, and I should have read that definition again. One is the clearance, one is the interference. Let's see which way it's, and then the shaft side. And we'll see if it picks up the up to next. So with the selected bodies, and it's set to auto select, well, let's just go ahead and put them in and see if it carries through. All right. So I would probably build this into the main sketch, or like I said, if I had a 3D sketch, I would drive quite a bit of this geometry with it. What do we have? Center line. I'll set to symmetry. And for a distance, let's just see what looks good. Maybe 50 millimeters. Okay. We'll select. All right. So if I go back to the hidden, so it did the press fit on this side. At least we think so. And then we're going to pick up the geometry for this. So I'm trying to put all of the geometry into the base that I can before I get kind of the stack up for the rest. All right, so we'll hide that one. And now we're ready for the tapped hole going into the vertical. And that's going to be an ANSI metric. Probably an M10 by 1.25, so not the coarsest, not the finest. And then up to next, probably not. Let's go 20 millimeters. We have 5 millimeters on the wall, and 20 millimeters, 23.75 deep. We'll be in that range. That means that we could use a 15 millimeter, maybe a little bit longer, and we would have that engagement. That only really gives me at 15 millimeters, though, the 1 times diameter. So 10 millimeters deep on a 10 millimeter thread. Might want to go a little bit more than that. So let's take it up to 30 millimeters and 25 millimeters so that I can at least get a little over the 1 times D. All right, so positions, and jump back in. And I'm looking for those center points. And when those go fully defined, recognizing the center points, they're now tied together. I think the whole wizard will go between the 2 bodies, so we'll go ahead and include that and see if it picks up our geometry. So 2 on the base, 1 on the front. That should just about cover it. All right, so the through holes then. 1 more S key. Design to the through, still a dowel, and then this is now the clearance side. And don't know that needs to be 30. We're going 15 millimeters through, so 15 millimeters with a little bit extra. We could use then a 25 or a 30 millimeter pin to find the intersection. And we'll set, yeah, I think 25 would probably be deep enough. And looking for that edge, finding its center, we'll set the body. All right, so let's take a look at what that looks like in hidden. So, oops, not sure what happened to that one. Oh, 1 millimeter, nice. I did see that. It looked exactly like 10, but we were doing. Oh, we were going to switch back over to ANSI inch anyway. All holes 5/16, and clearance. We'll stay with the 6. I think I'm getting those reversed. I'm going to have to go back and check those. before I hand it over to you, I'll make sure that those are correct. All right. So looking at this at this time is we press the pins in, the vertical slides over, we tighten the 3 screws, that comes into place. We tighten the 2 for the gusset, but we also need one to go through the front of the vertical just to pull it up tight and bring in the geometry. All right. So the other thing to keep in mind on the design point is every time I add one of these holes, add another piece of geometry, it's something else that's going to have an associated tolerance. So I'm trying not to get too carried away on you, but also putting in the enough of the design to make it functional. All right. So same thing, counterbore, and symmetric, socketed cap screw. And I think the M10 probably doesn't need to be. So I guess when I have the flange, if I was going to use M6s or M8s, I might do them all of the same. So I don't know that those are going to be M10s. I think we probably get away with an M6. We just need to align it and get it into position. All right, so counterbore, position, place it, and let's go normal to the sketch. All right, so I don't want it that tall. Again, if I have a flange, even if I shrink the flange, I'm not going to. I'm going to try not to get that engaged. So we'll go 50 millimeters. I can locate it to the origin, set it vertical. All right, and then for the depth, key, pick up our threaded hole, length symmetric, M6 by 1. And it doesn't need to be an up to next. We can again do the blind in condition. 12 millimeters deep, 6 millimeters is going to leave 9 millimeters. So if we had a 20 millimeter, 25 millimeter, that should be okay. We'll go ahead and check for it. All right. So that gives us location, gives us geometry, and then as we're looking through this also is the start of, if I am doing the tolerance, then I have either flatness as being the datum simulator, being able to set that down onto our surface plate, and then checking for parallelism, the perpendicularity to the face so that the flange is parallel to our base, and then finally the leg that is sticking out, that it has enough suitable rigidity geometry to hold itself up. All right, so last one. We'll do one more. I think those can stay. Since that was 10 millimeters, that'll give us 4 millimeters of wall thickness. So staying with the 6 millimeter depth, or 6 millimeter tapped counterboard and tapped hole. So the question here would be, do I need the precision of putting in a couple of pins? And since I don't really have the room, this might be a better spot to switch over to the countersink. All right, so a 6 millimeter countersink. And again, if I decide later on that this isn't the best course, then it's not that big of a deal to change it over to a counterboard and add the pins in. All right, so blind will be up to next. And positions, go to the top. And set those vertical. Yeah, I'm thinking the 25 millimeters would be okay. If I go with the center line, then those will stay symmetrical. All right, and then we're missing off of the base. See if we can pick up that other geometry. So no, I don't want to include that, so it becomes a construction line. Even though the whole wizard really doesn't mind the object lines for whatever reason, I'll still kind of pull it in with the center lines. All right, so one more S key. We'll stay with the metric. Pick up the M6 by 1. Not an up to next, so it goes to blind. 12 millimeters and 15 millimeters. I tend to stay away from the countersinks. We can put that in as a note if we need it, but the countersinks kind of pick up on the geometry, pick up on the CAM programs as extra noise. All right, so when we tighten this down, the countersinks come down, locate into the tapers, into the cones, and that provides at least a little bit of it's not going to rotate, it's not going to affect the geometry. All right, so the couple of times that I saw this, it's sticking out a little ways, so let's measure, and we'll see evaluate. So normal distance of 5 millimeters, looks like a DX of 5 millimeters, and thought that was 60. I had it at 80. Probably going to end up being 60. All right, so we go back into the layout. I find my dimension. Double click on the layout. Find my dimension. Double click on it. We update it to 60, and then rebuild, and it will update. And now it's sitting interior, which is a little bit more of what I expected. All right. So the final bits of geometry kind of followed my pattern pretty well. I missed the base holes, so let's go ahead and do a save real quick. So I missed the base, and then we need the through. So let's go back over here, and so that was given as a linear 22 from the end. All right, so we're going to have to line that up and make sure that it stays on center with the cam. All right, so having done that, the flange bushing that I picked, the housing ID, 8 millimeters, 11 millimeters, 11.03 for the OD for the press fit. So it looks like I need an 11 millimeter through. Yeah, I want to stay with the hole wizard on this because we're going to stay with the class of fit. All right, so ANSI metric, the dowel, and one of the reasons that I pulled out. All right, so it didn't do a hole size for 11 millimeter. Interesting. So that's always a little bit of a concern. Well, it is picking up a dowel. So that one probably isn't going to be a standard. All right, so we'll have to treat that one separately, or I'll look into it a little bit more and tie it back together. And up to next, the position. And horizontal to the origin, 22 millimeters back. Okay, didn't exactly want it to dimension. 2 millimeters, and we go ahead and hit OK. Alright, so last pieces of geometry on this one. Let's see, we had a couple of radiuses. We also have the 20 millimeters for the 4 holes. And need a position. Well, they're going to be at the centers, so always a little hesitant. I want to put the fillets in after. So since they're 20 millimeters all the way around, I'm going to go for midpoints. Oops, don't need that one. And 20 for the vertical. And then to locate, we pick up the mirror and the mirror, and then this is going to be extruded cut through. Alright, so I know there's going to be a few more fillets, but if I do the fillets last and as a group, then I can treat them, let's see, 20 millimeters. I can treat them as, you know, kind of the last. If there's any issues, any problems with the design, then I don't have to include the fillets in the overall you know, analysis and the overall review. All right. So, well, that's running a little longer than I expected. So, the end result is that I end up with a gusset. And so, right before I kick these out to a separate assembly, we have the let me tie it back to the assembly a little bit. That'll help me keep track of it. So the cap, and then pretty much that one will be the base. All right. So the end result is I have this part with all of these individual pieces, and I can extract them out and make drawings of the individuals, but I really am not going to be able to do the fasteners. I'm not going to be able to do the types of things that I would like to do. So we have on the right click, insert into new part, which doesn't really help me, and we have save bodies. So they're going to go to the metric template. I have it set to ask me which template to use, and then which assembly. So apparently I don't have a metric assembly handy. So that one's probably the closest. Yeah, we'll stay with it. All right. So it gives me this save bodies, and auto assign names pulls the names that I gave the bodies. And we need to go ahead and create the assembly. So this is the cam follower base. I'm trying not to write a novel into my descriptions, into my names. Right, so it's showing each of the items where they're located. What else do I need? Don't really care about the visual properties. The origin location at the default should be fine. So when I go ahead and save this, keep my fingers crossed. It clicks, it whirs. We tell it to rebuild and save the document. And after it's done, I don't think I told it to consume anything. Oh, maybe I did. Probably should check that. All right. And the assembly. Oh, that was the one I missed. So the consume cut bodies, yeah, probably not. All right, so I would like to be able to modify and work with those if I need them. So now my bodies are still there. And one of the rules is that anything that gets built after this save bodies features or feature does not propagate downstream to the rest of the models. The other thing is I do not want to suppress this. If you suppress the save bodies, then it takes all of these names, the solid bodies names, and it sets them back to whatever the last feature was that was added. That's kind of a pain to also correct for. So even just like the top-down assembly, it comes with tricks and traps, there comes with issues. And so if I need to make a change that doesn't include one of these, I can perform a rollback, and the rollback is legitimate, but the no-no is suppressing the save bodies. All right, so what this did for me after all of that, I'm going to go ahead and save one more time, is when I open up the assembly, now I have something very similar to a top-down assembly model where these are virtual components or assembly components. The advantage here is that they're all tied back to that MB, that model, multi-body part. Okay, so the base vertical, the cap, and the components. Each of these is now a separate part. If I go back into the folder and into the base, this is the parent, these are the children, and that is the assembly that all of these created. All right, so as you go through the process, it gives you a chance to make those alignments to very quickly change and adjust. And so when I make my decisions on the flange and I make my decisions on the gusset and tie those in, that geometry will update and it will propagate downstream to the other items. All right, so that is what I need you to be aware of, is that when you open up those parts, it should automatically open up this multi-body part, because all of the, actually this one, it should open up this one by default, by process, because it needs to have this geometry available. So when we take it into the drawing, rather than picking each of the individual solid bodies, we're now going to pick each of those parts. All right. So as a strategy, maybe a little quicker than building each of the parts and assembling them and then making adjustments as we go. We'll do the trade-off with the follower on the top down. All right. So when I get this into a drawing, then you will have the task of putting the tolerances on it.